This is chapter 2, which is about properties of fluids. I was finished with chapter 1, which was about introduction, basic concepts, and chapter 2 from your book, Fluid Mechanics, Fundamentals and Application, will deal mainly with properties of fluid, and this is the first short lecture of it. Okay, so the chapter topics are, as you can see, introduction, density and specific gravity, vapor pressure and cavitation, energy and specific heats, compressibility and speed of sound, viscosity, surface tension, and capillary effect. So, in this lecture, I'm going to cover the first two sections, which are introduction and density and specific gravity. So those are the two sections I'm going to cover in this lecture. So let me start with a simple question or questions that I know that you heard them before. So let me ask you, what do we mean by property, intensive property, extensive property, and specific property? So take a few seconds to think about this question or those questions. Okay, so you know that any characteristic of a system is called property. يعني characteristic معناتها خاصية من خواص system. So some familiar properties are what? They are pressure, temperature, volume, and mass. So if this is your system here, so mass, volume, temperature, pressure, and density, those all are different properties of the system. We can have at least two types of properties, intensive and extensive. So what do we mean by intensive properties? So intensive properties are those that are independent of the mass of the system, okay, or like the intent of the system. So intensive properties are those that are independent of the mass of the system. For example, as you can see, temperature, pressure, and density, those are intensive properties. And it doesn't matter if you divide the system into half, the temperature didn't change, the pressure didn't change, the density didn't change in each part of the system. However, the extensive properties, they changed. If you split the system to half, now you have half the volume and half the mass. So the mass and the volume, they did change. Now, there is an important thing to draw your attention to, but I think we'll do it in the next slide. Okay, so let me continue then. So extensive properties are those whose values depend on the size or extent of the system. So extensive properties are those whose values depend on the size or extent of the system. And if you take an extensive property and you divide it by mass, or the extensive property per unit mass, is called a specific property. So if you want to, remember it easily, just remember intensive, independent. They both start with the letter I. Okay, so if you got confused, so intensive, they are independent of the mass of the system. Let me go on. Now, let me remind you by what do we mean with density, specific volume, specific gravity, and specific weight. And since I have this picture here, this is an indication that there are movies related to the subject that you can watch. In the first chapter, I've showed you some movies and I explained them to you, short clips. So the same thing applies here. So I want you to watch those short movie clips by yourself this time. Okay, so let's start with density. So density is defined as the mass per unit volume. You know this. So rho, which is density, is equal mass per volume. And the unit of density is, for example, the SI system is kilogram per meter cube. And if you take the reciprocal of the density, then you will have the specific volume, okay, which is defined as the volume per unit mass. Suppose you have a volume here, as you can see, of 12 meter cube. You have a mass of 3 kilogram. Then the density is equal to what? Is equal to mass divided by volume, which is equal to 0.25 kilogram per meter cube. And the specific volume is just the reciprocal of the density. So it is 1 over 0.25. That will give you 4 meter cube per kilogram. The thing that I said a minute ago I want to draw your attention to is the notation that is used in your book. Whenever your book is using the big V, as you can see here, big V, this is the volume. Whenever he is using the small v, as you can see, this is the specific volume, which is the volume per unit mass. Okay, so please uh, take, let us say, a note of this. Big V volume, small v, specific volume, which is volume per unit mass. Now, let me ask you a simple question, a basic one. Which is heavier, a kilogram of water or a kilogram of mercury? طبعا knowing that mercury is much more dense than water. The density of mercury is 13.6 times the density of water. So which is heavier, kilogram of water or a kilogram of mercury? Think about it. Another question, which is heavier, a kilogram of water or a kilogram of gasoline? gasoline اللي هو البترول اللي نحطه في السيارة. And put in mind that the density of the gasoline is, or the specific gravity of gasoline is less. The density of gasoline is less. It is like 70% the density of water. Okay, now this is another question. Which is heavier, a liter of water or a liter of mercury? Again, the density of mercury is 13.6 times the density of water. And now the last question, which is heavier, a liter of water or a liter of gasoline? Again, put in your mind that gasoline is less dense. The density of gasoline is around 70% the density of water. Okay, so I will keep those questions for you to think about for the time being. And the last question that I'm not going to answer for you, is it easier for you to swim in salty water or in fresh water? And why? If you say it's easier to swim in salty water, then you have to tell me why. If you say uh, it's easier to swim in fresh water, you have to tell me why. Okay, so let us now talk about specific gravity, or also it is called relative density. So specific gravity is defined as the ratio of the density of a substance to the density of some standard substance at specific temperature. Usually we use water at 4 degrees centigrade, where the density of it is equal to 1000 kilogram per meter cube. So the specific gravity, Sg, is equal to the density of substance divided by the density of water at 4 degrees centigrade, which is at 1000 kilogram per meter cube. So here's a table, table 2-1, that shows the specific gravity of different substances at 20 degrees centigrade at 1 atmosphere. So water got a 1 specific gravity because it is like 1000 by 1000 will give you 1. Blood has a specific gravity of 1.06. Seawater 1.025. Then you have gasoline that I talked about a minute ago, 0.68. And you go on, mercury is 13.6. Wood, this type of wood, we have two different types of wood. We have gold, which is almost 20 times more dense than water, ice, and air. So what do we learn from this? We learn the following. The specific gravity or relative density will tell you how the material or how the subject is, dense relative to water. So if the specific gravity of a subject is greater than 1, this means it is more dense than water. It is more dense than water. The density of it will be more than the density of water. If it is less than 1, this means it is less dense than water and will float on the water. This is why, for example, as you know, that wood will float on water. The density of it is less, so the specific gravity of it is less. And however, those with specific gravity more than 1, for example, you have the gold. It is 19 times more dense than water, and if you put it in water, it will just sink there. So the specific gravity then can be used as a measure of the density of the substance compared to the density of water. If it is more than 1, it is more dense, it will sink. If it is less than 1, it is less dense, it will float. Okay? And please note the following. I have air here, and the specific gravity of air is 0.001204. Okay? Which means it is much less than the density of water. So from now on, I want you to note this. You know that the density of water is here as it is shown. We take it as 1000 kilogram per meter cube. So from now on, you can consider the density of water to be like 1 kilogram per meter cube, which is 1,000th of the density of water. 1 على 1000 من كثافة الماء. Okay, so the density of air, as you can see, it is almost 1 kilogram per meter cube. If you want to be more specific, it is 1.2 kilogram per meter cube. Okay, تقريبا 1 على 1000 من كثافة الماء. So if I go back to those questions, okay, let me go back to them. So which is heavier, kilogram of water or kilogram of mercury? It doesn't matter the density of water or mercury. I'm talking about a mass, so the mass is the same. So they have the same, let us say, mass, okay? And the same weight طبعا here. Which is heavier, a kilogram of water or kilogram of gasoline? It is the same. Which is heavier, a liter of water or a liter of mercury? طبعا the liter of mercury will be more heavy by 13.6 times than the water. And which is heavier, a liter of water or a liter of gasoline? For sure water, and it will be heavier by 30% because the density of gasoline is less than the density of water. Is it easier to swim in salty water or in fresh water? Again, I will leave this for you. I'm not going to answer it. Now, there is a property which is called specific weight or weight density, and it is equal to the volume of a substance divided, it is the weight divided by the volume of the substance. So gamma is equal to W, which is weight, divided by volume. But we know that weight is equal to m times g divided by volume. And you know that the mass is equal to what? Is equal to rho v, and this is by, so this is the mass, this is the volume, volume cancels, and then I get rho g. Okay, this is how we got it to be equal to rho g. So the specific weight or the weight density is equal to the density times the acceleration due to gravity. Okay, this is how we define it and how we calculate it. Let me ask you a simple question now, very simple question. What is the mass of air in your room? Suppose the dimension of your room is 4 times 5 times 6 meters. So how can you get the mass of the air in the room? So you know that mass is equal to density times volume. Okay, and we have just said the density of air is around 1.2 kilogram per meter cube, and the volume, if you just multiply 4 by 5 by 6, you will get something like, how much this, 120 I believe, meter cube. So if you multiply this, meter cube cancels meter cube, and you will get something around 100, yeah, this will be 144 kilograms of air. So if these are the dimensions of your room, very simple calculation will tell you that you will have around 140 kilograms of air by using the definition of this formula. Mass is equal to density times volume. I will tell you later why I asked you to do this. Okay, now, how do we call, or what do we call, the equation that relates pressure, temperature, and density of a substance? What do we call it? Take a minute, take a few seconds, and think about what do we call this equation. Okay, so an equation that relates the pressure, temperature, and density or specific volume of a substance is called the equation or an equation of state. And you know that the most well-known equation of the state is the ideal gas law. And if I ask you to write the ideal gas law, you might write the following. You might tell me BV equals nRT. Okay, BV equals nRT. And if I ask you what is P, you will say P is the absolute pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the absolute temperature. Now, your book doesn't call R gas constant, but according to this equation, he will put a U here, and this RU, he will call it universal gas constant. Okay, universal gas constant. So if you want to use this form, then you have to write it like this. P capital V capital equals N capital R with sub U, which is universal gas constant. And this is the one that you are familiar with, which is 8.314, etc. Okay, so this is the universal. It is the same for all the gases. However, now to get the form of the equation in your book, we'll do a little bit of adjustments here. So suppose I will take this equation and I will divide it by mass. So I will divide the volume by mass, number of moles by mass, RUT. So I will just divide it the left hand side and the right hand side by mass, so I didn't change the equation. So from here you know that V by M, as I told you a minute ago, this is the small v, the specific volume. So this is P and V. This is the big V, this is the small v, equal to. Now, N by M, this is moles, and this is mass kilograms. So kilogram per moles, what is this? This is what do we call the molar mass or molecular weight. Okay? But it is the reciprocal of it. It is not M by N. It is not mass by moles. It is moles by, it is mass here down and moles up. So I will give it this as M. So M is the molar mass or molecular weight, but it is the reciprocal of it because moles up and mass down. So this is 1 over M, this is RU, and this is T. Now I will just rewrite this here. So BV equals, and I will group RU divided by M together. This is M, and this is T. And this is RU by M is called gas constant. So the notation used in your book that RU by M is called gas constant, and the equation at the end will be B V small is equal to RT. So this is the ideal gas law according to your book. This is the absolute pressure. This is the specific volume, which is volume per unit mass. This is the gas constant, which is different for different gases, which is equal to the universal gas constant divided by the molecular mass. And finally, I have the absolute temperature. Okay? BV equals RT, or if you want, you can say this is P divided by, you know that the reciprocal of this is straw equal to RT. So finally, P is equal to rho density RT. So this is another form of the universal gas constant. So it is either you write this form here, BV equals nRT, but please note that this V is volume, number of moles, universal gas constant, this RU. However, here BV equals RT, this form, this V is specific volume, and this is gas constant. So let me go to the next slide to make things even more clear for you. So the simplest equation of a state is called the ideal gas equation of a state, as I have just said, or simply the ideal gas relation. And the gas that obeys this relation is called the ideal gas. And this is the equation I've just showed you in the previous slide. BV equals RT, or P is equal to rho RT. And I showed you the relation between this equation, this form, and the BV equals nRT form. So where P is the absolute pressure, V is the specific volume as I told you, T is the absolute temperature, rho is the density, and R is the gas constant. R is the gas constant in this equation. Okay, it is not the universal gas constant. Now he's telling you the gas constant R is different for each gas and is determined from this equation, where Ru is the universal gas constant whose value is 8.314 kilojoule per kilomole Kelvin and equal to this. The values of R and M for several substances are given in table A-1, and I'm going to upload this table as well for you on Blackboard. So this is the table just for demonstration now. So for air, for example, this is the molar mass, and this is the R, the gas constant. So if you are using this form, PV equals RT, then you use this R given here, and you use this, if you will use this form, then you don't need to use this, for example. But if you will use this form, BV equals nRT, this is the universal gas constant, then you will need these two, because you know that R is equal to RU divided by N. Okay, you got it now? This is the difference between the universal gas constant and the gas constant and these two forms of the equation. Just let me remind you about the Kelvin scale, the Rankine scale, etc. So the thermodynamic temperature scale, the SI, is the Kelvin scale. And the temperature unit in the scale is called the Kelvin, designated by K. As you can see, this is capital K. In the English system, it is the Rankine scale, and the temperature unit in the scale is Rankine or R. How to convert Celsius to Kelvin, how to convert Fahrenheit to Rankine. This is easy. I will just go through it quickly. So you know that if you want to convert from Celsius to Kelvin, you just add 273.15, and then if you have, for example, the temperature Rankine, you divide it by 1.8, you will get it in Kelvin, and then from Fahrenheit to Rankine, you add this much, and if you have the Kelvin and you want to convert it to Rankine, you multiply by 1.8. You have studied this many times in the thermodynamics course and in the introduction course. This is the last slide, and this is an exercise for you. You notice that this is similar to the one that we have done it a few minutes ago. Determine the density, the specific gravity, and the mass of air in a room whose dimensions are 4 times 5 times 6. The pressure is given, and the temperature is given. So this is exactly the same, but now more details are given. You have the pressure and temperature. You don't have the density, you don't have the specific gravity, and we need the mass. So how to do this? So first, you have to use the equation of state, the ideal gas law. So you cannot assume the density to be 1 or 1.2. You have some information. So the first thing, you have to determine the density. Okay, so you know that rho, or let me say that P is equal to rho RT, as we have just done it. So rho is equal to P over RT. Okay, so P is given to you, R is given to you, just go to the table. T is given to you. You can get the density. And if you have the density, you know how to get the specific gravity. Okay. And finally, the mass is just as we have done it before, mass is equal to rho times V. So I want you to do this and compare your answer with the example that we have done before. So in this lecture, I covered the main thing, which is the density and the specific gravity of the substances and little bit of the introduction. So this ends this lecture.